To describe a straight line in three-dimensional space, we need two pieces of information. We need one point that lies on the line and one direction vector, which tells us which way the line points. To describe a flat plane in three-dimensional space, we also need two pieces of information. We need one point that lies on the plane and one normal vector, which is a vector that points straight out, perpendicular to the plane. Let's work through a full example together, starting with the line. Suppose our point on the line is P with coordinates 1, 2, -1. Suppose our direction vector is D with components 2, -1, 3. In words, the vector equation of a line says the position on the line equals the starting point plus a number t times the direction vector. In symbols, we write r equals the vector 1, 2, -1 plus t times the vector 2, -1, 3. We can also split this into three separate parametric equations, one for each coordinate. X equals 1 plus 2t, E equals 2 minus t, Z equals -1 plus 3t. On screen, watch this line as a flat two-dimensional sketch first, showing just the direction arrow from the point, then watch it rotate into the full three-dimensional picture so you can see the same arrow living in space. Now let's build the plane using the same point 1, 2, -1 and a normal vector, n with components 3, -2, 1. In words, the equation of a plane says the normal vector dotted with the vector from our known point to any general point x, y, z equals 0. In symbols, we write 3 times the quantity x minus 1 plus -2 times the quantity y minus 2 plus 1 times the quantity z plus 1 equals 0. Let's expand each bracket carefully with no steps skipped. 3 times the quantity x minus 1 gives 3x minus 3. -2 times the quantity y minus 2 gives -2y plus 4. 1 times the quantity z plus 1 gives z plus 1. Now we add all these pieces together and combine the plane numbers. -3 plus 4 plus 1 gives +2, so the equation of the plane simplifies to 3x minus 2y plus z plus 2 equals 0. On screen, watch the plane appear first as a flat two-dimensional cross-section, then watch it tilt and expand into the full three-dimensional plane with the normal vector sticking straight out of it, so you can see how the arrow controls the tilt of the plane. Now let's check the line equation by substituting t equals 0. X equals 1 plus 2 times 0, which gives 1. Y equals 2 minus 0, which gives 2. Z equals -1 plus 3 times 0, which gives -1. This matches our original point 1, 2, -1, so the line equation checks out. Now let's check the plane equation by substituting the original point back in. 3 times 1 minus 2 times 2 plus -1 plus 2. That gives 3 minus 4 minus 1 plus 2. Adding these together gives 0, exactly as the plane equation requires. Since both the line and the plane pass their checks, we can be confident that our equations correctly describe the line and the plane through the given point, using the direction vector and the normal vector.